Okay, so today we're going to be doing three things. We're going to be looking at two machine learning algorithms, the neural network and the support vector machine, both of which I think are amongst the most complicated of the widely used machine learning algorithms, thus I have saved it for last. And then in actually doing your homework for next week, it occurred to me that you might need to know more about R than you actually know yet. And so I'm going to go through some additional material on how R actually works, because this is the first time we're going to be using R to analyze. It's going to be calling Java functions. Weka is written in Java, and so there's this complication of multiple languages going on, and you need to know a little more than you do about how to deal with that. Okay. Kristen? Thanks. All right, so neural networks. This is probably the oldest of the machine learning techniques, and there are a lot of different kinds of neural networks. This one is called a feed-forward neural network, and it has its origins and an understanding as to how the human brain works, that there are neurons and they fire signals, and if enough signals fire, they activate other neurons, which in turn combine with yet more neurons, and somehow you magically get thought out of that. And I am not enough of a biologist to have any idea whether that's an accurate current representation of how the human brain works, but it's still how neural networks work. So I'm going to be using Mathematica to demonstrate this. And the idea here is that one starts with some piece of data. Okay? So here's, in this model we have three features. Okay? And we then combine those three features in some sort of what's called an affine transformation, meaning basically a linear combination of these features. We might add in a constant term at some point, and those produce more features. And then we do another, we take the, let's see if I can explain this. Let's take this value here. We're going to take the sum of some weight times this value plus some weight times this value plus some weight times this value. And then we're going to take that overall sum and squash it so that it is some value between 0 and 1. So we've got the combination of an affine transformation, a linear transformation basically, and a squashing function. And you've seen squashing functions. Basically, the CDF of any probability distribution is a squashing function. Whatever value you put in, it says, well, the cumulative probability of that is somewhere between 0 and 1. And so oftentimes you'll actually see probability functions used here. You might see the normal distribution used, or there's a distribution involving hyperbolic tangents that you haven't seen, but it's useful. In any event, the idea is that one takes these what are called hidden nodes. They're hidden because all the user sees is they see these features and they see the final class that actually results in the real world. That's their observed data. And we create these hidden layers of data, which are created, as I said, by this sort of combination of take the data, add it up, squash it, and then basically do it again. Have another layer where we take the results of this first hidden layer, add them up, squash them, and then do it a final time with a final squash to make a prediction as to whether something's going to be a 0 or a 1, or how close to 0 or 1 it's going to be. And so that the trick involved here is you have to know what weights to attach to each of these connections. So for example, if this were a 6 and this were a 4 and this were a 2, that might give you at the end a very bad prediction of what this value was going to be. Whereas if this were a 2 and this were a -1 and this were a -3, that might give you a much better prediction, not just on this particular piece of data, but you're throwing all the data at it and seeing what the cumulative error is. And so I know this seems really simple.